All right, all right, all right. It's physics time. We're about to talk about velocity and speed, but first, let's go ahead and summarize uh, position, distance, displacement, and then some vectors and scalars. So these are things that we might have figured out from the last sessions. We've got distance as compared to displacement. Distance is like tracking the number of steps or miles. Focus is on the actual journey, but not the direction so much. Displacement does care about the direction because parts can cancel out. And then it also thinks more in terms of the difference between the start and the end points. Okay, and then this kind of helps us understand scalars and vectors. Scalars are magnitude only. Scalars, well, let's see, let's make sure we understand magnitude. Magnitude means size or amount, but some examples of scalars, distance, speed, temperature, time, and energy. So it's like how far, how fast, how much, not paying attention to direction. Vectors do pay attention to both magnitude and direction. It's not just direction. Vectors have to do magnitude and direction. So some examples of that would be displacement, velocity, acceleration, force, momentum. So how far, how fast, yes, but by paying attention to direction, as we said, things can cancel out. And then here, position. Position is where you are relative to some reference point, like a house or a tree. When we start talking about graphs, and we'll do that very, very soon, we're going to see that the 0 point on a position time graph is not necessarily where we start. That'd be like on the vertical axis, but just some reference point. But we'll get there. We'll get there. All right, let's go on to velocity and speed. So we got our learning targets, velocity and speed. I can distinguish between velocity and speed and calculate each. So displacement over time. We've already talked about displacement. That was the change in position. If we take that and we say, well, how long did it take me to start here and then end here? Did I change these positions very, very quickly or in a very, very short amount of time? So that is going to be taking time into account. That's called velocity. When you divide velocity, or excuse me, when you take velocity and you divide change in position, your displacement, divided by the time interval. And that is going to be the average velocity. We'll talk about instantaneous velocity in just a second. But what's nice is it's a very simple equation. You can rearrange things very easily, solving for d or for t or for v if you'd like. Okay, so d is equal to vt. If you've ever seen one of these pyramid dealies for equations, what you can do is you can like cover up, oh, I want to solve for d. So covering up d, I got v next to t, so I'm going to multiply v times t. All right. If you instead want to solve for v, you cover up v, cover up the v, and then you say, oh, look, it's d over t. Oh, okay, so I'm going to divide. It's like this is like a division, right? And then solving for time, I can cover up the t, and then look, I've got d over v. D over v, the displacement divided by the velocity. You can do it that way, or honestly, I just use this equation and just rearrange it. It's whatever's most comfortable for you. But if it's a setup like an A is equal to B times C setup, you'd say A up here and then B and C down there. The thing's multiplied down there. If it's like other things like adding and subtracting and stuff, it doesn't work here. But that's okay, because we're just talking about D is equal to VT. Boom. In fact, let's do some example problems. What? Mayung walked down the 45-meter hallway to physics class in 53 seconds. How fast was he walking? And then how long would it take Daniel, who walks at 1.1 meters per second, to travel that same distance? So the first thing we're going to do is visualize what's going on. We're saying, okay, what's the deal? Mayung has some type of distance or displacement. So let's go ahead and list out that information. He is traveling down the hallway, and we know it takes a certain amount of time. So we're making a list of variables. We're just going to say, oh, let's solve for v. Velocity is equal to question mark. So let me list out all my variables, and including my unknown, what I'm searching for. And then I say, oh, well, I'm just going to say v is equal to d over t. I don't even need to worry about it, but I can do the cover out the v, and I get d over t, right? And then, after I've rearranged my equation, I can go in and plug in and solve. So I get 45 meters over 53 seconds, and I calculate that to be velocity is 0.85 meters per second. That's for my own. Now, Daniel is walking down the hall, slightly faster, 1.1 meters per second. And we're wondering how long it takes Daniel to travel this distance. So it sounds like we're looking for the time. We're looking for the time. We have 1.1 meters per second. That's the velocity. Oh, what's the displacement? I only got one number here. What? I don't know. Whoa, wait a minute. All right, to travel that same distance. Oh, so we're going to use the same d as before. Okay, we're still going to use 45 meters. Still going to use 45 meters. Great. All right. So this time I've got to rearrange this equation, or I got to solve for t, whichever way you want to think of it. T is equal to d over v. As I said, I just prefer to rearrange the equation. But you want to do that before you start plugging in. And as we get into more and more complicated stuff, that will be very much important. Okay, so t is equal to d over v. Plug in, we get 45 meters divided by 1.1 meters per second, and chug, we get time is equal to 41 seconds. Woohoo! Physics. Now let's talk about speed. That was more about displacement, although I think I did use the word distance in there. Shame. It's hard to distinguish d. Is d distance or d displacement? You do have to be careful, and I should have been a little more specific on there. But let's go ahead and talk about speed. You say speed. Well, I know about that. Like, if you've ever been in a car before, you have some concept of how fast you're going, right? Now, how do you know how fast you're going? Well, you can look out the window and say, I'm passing by a bunch of buildings, bunch of trees, bunch of whatever's very quickly or kind of more slowly, right? Okay, so you think of speed is distance traveled divided by the time elapsed. And you say, this equation sounds just like for velocity. Yes, but remember, this is distance as opposed to displacement. This is distance over time. Velocity is displacement over time. There's the difference, because this is independent of the direction of motion. So you think of your speedometer. I mentioned the speedometer earlier. The speedometer tells you how fast you're going. It does not care about what path you're taking. Generally speaking, your car, the components in your car do not care about what path you take, do not care about the direction you're going in. They really only care about the path. So like the odometer is keeping track of how many miles you went. The speedometer is just telling you how fast. Neither of them pay attention to direction. Now, if you have a GPS worked into your car, which most cars do now, those would, but those are not mechanical really aspects of the car. Those are like add-ons you can think of. Okay, so scalar, as we said, no, we're not paying attention to direction. We got just a speedometer here. And the units for speed are also going to be meters per second, just like for velocity. Interesting. All right, so there are different types of speed. There's average and there's instantaneous. I mentioned that there are these distinctions. Average speed means the total distance divided by the total time. Okay, it's what we would normally think of. We go on a trip, we say, hey, I traveled out from Virginia to Minnesota, and that's about 1,500 miles, and it took me this many hours of driving, and I just take that total distance divided by the total time. Easy, right? Okay, instantaneous speed is similar, but it's also going to be different. Instantaneous speed is how fast we're going at that exact moment. So not the overall distance divided by the overall time, it's saying how fast you're going at that moment. Okay, so to clarify, think about this. When you're driving your car, or when you're walking, or when you're doing whatever, are you always staying at a nice constant speed? Or is there traffic? You just have to speed up, you have to slow down, and so on. Okay, so imagine you're going to school. It's physics day, and you're like, oh man, I just want to get to school. I just want to get there and sit in physics. Woo! And then you're stuck behind a school bus. Has that ever happened to you? It happens to me a lot. Yikes, stuck behind a school bus. I'm like, oh. So I'm going super slowly. I'm much of the time I'm stopped because people are getting on and off. And then you move along, and then the school bus stops again. You're like, oh my goodness, I'm gonna be late. I'm gonna be late for physics. No. Finally, the school bus turns off, and you're like, oh man, I gotta I'm gonna put the pedal to the metal here. So I go a little bit faster than I really should be going. In a neighborhood, it's supposed to be like 25, right? And then what happens? There's flashing red and blue lights behind you. Cop pulls you over going at 35 miles per hour and at 25. Okay? Police officer comes up and says, do you have any idea how fast you're going? Well, you say, actually, officer, yes, I do. You see, speed is distance over time. I happen to know how far I am from my house. It's this many miles. And I happen to know when I started because I looked at the clock when I started. And it's been this many minutes. Let me get out my calculator. I'll do the conversions for you, officer. No problem. No problem. And you tap it into your calculator. And you say, yeah, according to this, my speed was 22 miles per hour. I guess I'm free to go, right? Is that what's going to happen? The officer just says, no, physics, you got me again. Go on ahead. Woo, go ahead, right? No, I would not try that with a police officer. That would be bad news. I'd be like, step out of the car, breathe into this. Yeah, that would not be what the police officer is talking about. The police officer is talking about the instantaneous speed. Instantaneous speed is how fast you're going at that particular moment. Now, how do we say that particular moment? Well, instead of saying I'm driving for an hour, let's shrink down that time. Maybe it's now half an hour. That's too long. Maybe we can shrink it down even more. Maybe 10 minutes, maybe 2 minutes, maybe 1 minute, 30 seconds, 2 seconds, 1 second. You keep shrinking it down more and more. That's actually called in calculus, or maybe I think pre-calculus when they'll talk about it, taking the limit. Now, if you've never heard of this before, if you're not in pre-calc, don't worry, don't forget. Oh, I'm gonna have to do limits, what is this? If you are in calculus and you're like, oh God, please no limits, don't worry about it. I'm just trying to reference something that you might have heard of before. Anyhow, it's when you shrink down the time interval and you end up shrinking down the distance, but shrink down the time so it's almost zero. Okay, it's just taking the instantaneous. When we deal with graphs, we can also talk about tangent lines to the curve, but we're not actually going to be doing limits, as I said. Okay, all right. Instantaneous velocity is basically the same idea as the way we find instantaneous speed. Okay, delta D for displacement divided by time as time approaches zero. We're not actually doing limits, but it's just the idea of it's a very, very short time interval. Okay, in fact, the magnitude of instantaneous velocity is going to equal the instantaneous speed. So, okay, that's cool. All right, so let's make sure we understand velocity versus speed. So, how can we remember the difference? Velocity is a vector, and speed is a scalar. I wonder if there's a clever way of remembering that. Trying to come up with something. Is that the only difference between them? Just, oh, they got different words. Well, think about it this way. Can an object that is not moving at a constant velocity have a constant speed? So, not moving at a constant velocity, that means your velocity is changing. Can you have a constant speed? So, a changing velocity, but a constant speed. So, I want you to think about that. Can I have a changing velocity, but a constant speed? So, speed is how fast I'm going, but velocity is going to be how fast I'm going in a particular direction. So can I keep my speed constant but end up changing something about velocity? Could I change my direction? If I change my direction, is my velocity going to be constant anymore? I'd say no, it's not. But my speed could still be constant. Like if I put on the cruise control, then my speed is nice and constant, but I can still turn the wheel, right? I can still change the direction I'm going in. Now, does it work the other way? Can I have a changing speed but a constant velocity? Now, this is where a lot of people get confused. They say, oh yeah, I just gotta, I want a changing speed, so I'm speeding up, but I just stay in the same direction, right? No. Remember, velocity is how fast and direction. It's both of those. Right, it's velocity is both how fast and direction. Oh, that means class is about to start. I got to get going. Okay, so if we have a constant velocity, can we have a changing speed? No, no, we can't. If velocity is fixed, that means not only direction is fixed, but also how fast we're going. Okay, good stuff. Good stuff. Let's see. Do a think, pair, share. So let's see. Come on up. Woo-hoo. Fair was working on lesson plans the other day when his computer went out. Depressed at the idea that he couldn't do physics, he decided to go for a run around the track. Yeah, not really likely. I exercise on a daily basis, but I don't really go for runs. Figuring that each time around the track was 0.25 miles, he made 6 laps in 15 minutes. And I'd be happy to be going that fast. I don't actually run that fast. So I'm sure some of you are like, oh, that's no big deal, Fair. But assuming he moved at a constant rate, what was Fair's average speed and what was his average velocity? So go ahead and crunch those numbers. So a reminder that displacement is where you start to where you end up. Distance is the total path that you take, right? Keep that in mind. So average speed is going to be distance divided by time. So if I did, let's see, if I did 6 laps, let's see, that's 0.25 miles each. So that's going to be 1.5 miles. Okay, and that took me 15 minutes. 15 minutes is essentially, well, no, it is a quarter of an hour. Okay, so 1.5 miles divided by 0.25 hours. Let's go ahead and get out our calculators for that. 1.5 divided by 0.25, yeah, 6 miles an hour. Okay, I'd be happy if I could make it around the track like that. Okay, what's my average velocity? Oh, is it also 6 miles an hour, just like, north or this way or whatever? No. The displacement is where I start to where I end up. So if I start in one spot on the track and I go around once and I end up back there, what's my displacement going to be? It's going to be 0. Displacement is 0. What if I do that 2 times? Still 0. 3 times, 4 times, 5 times, 6 times. If I do it 100 times, yeah, in a golf cart, okay? If I do that 100 times, my displacement is still going to be 0, so that means my average velocity is also going to be 0. Okay, and now we got to come to a summarizing point, and we can. Oh, this was just a fun little meme. Is anything wrong with this slide? Velociraptor is equal to Distanceraptor divided by Timeraptor. Okay, is there anything wrong with this equation? Hint, there is. And then go ahead and summarize other things about speed and velocity. Physics.